Good afternoon, my name is Samuel Hui, and today I'll be going over parts B and part C of question 3 of exam 2. So, in problem B, we are told that there's a block that's at the bottom of a surface that's inclined by an angle theta, and it makes contact with a spring at the bottom of the incline as well, and it compresses that spring not only by a distance of x, but also by 2x. And problem B wants us to find the distance it goes up the incline when the block is released. So we can use what we know about the law of conservation of energy in any system to set up our equation of how we might go about doing this. And since we know that the block doesn't move when it comes to rest after it travels a distance and at the beginning, we can cancel out kinetic energy. And since the problem doesn't say that there's any external work forces, we can cancel that out, so we're left with potential energy on both sides. Now, there are two types of potential energy we need to look at, which is elastic potential energy due to a spring and gravitational potential energy. Energy for elastic potential energy is just 1/2 times the spring constant times however much it's been compressed squared. It's compressed by x plus 2x, so 3x, and we square that, and that's our potential energy by spring. For gravitational potential energy, we can set this height, the initial height, to 0, so that our final height ends up being whatever distance is traveled by sine theta due to trigonometry. So that would be d sine theta. And using this as a reference for what gravitational potential energy is, we get that there is no initial potential energy, which means that our final potential energy ends up being mg d sine theta. Now, in part A, we found out that x is equal to mg sine theta over k, so we can plug that in to this part and simplify this entire expression to be 9 k m squared g squared sine squared theta over 2k squared equals mg d sine theta. And you can check my math for this if you're not sure if you can get your answers right. And we can evaluate for d. The k's cancel out, and we're left with 1k at the denominator. 1m and 1g cancel out on both sides. And same for 1 sine on each side. And we're left with d is equal to 9mg sine theta over 2k, and that is our final answer for B. Now let's go on to find out the answer to problem C. So we're given the same incline and the same spring at the bottom. The only difference now is that there's another spring at the top, and the block begins at the top and compresses that spring by distance x. The distance from between the natural lengths of each spring is also x, and it slides down the block and comes to rest and touches the bottom spring without compressing it. And the reason why it does this is because now the incline has friction. So we need to find out what the coefficient of kinetic friction on the incline is. Again, we can use what we know about law of conservation of energy and set up our equation. And since the block isn't moving at the beginning and end of this problem, like in the last problem, we can ignore kinetic energy. So we're left with work external forces and potential energy, and we need to consider the same potential energies again. At the beginning, the block compresses the spring by distance x, so elastic potential energy ends up being 1/2 kx squared. And we can set the final height of this to be 0, so that the initial height will be the distance it travels times sine of theta. Why did I do that? So we end up having no gravitational potential energy at the bottom. And we end up getting the top is 2x sine of theta equals mgh. So that just ends up being 2x mg sine of theta. Now we need to worry about our work external forces. And because the problem says that there's friction this time, this quantity just ends up being work lost to thermal energy of friction, which is just force of friction times the distance it travels, which is 2x, times cos of the angle between its motion and the force acted upon the block. What is the force acted upon the block, though? We need to find that out. We can draw a free body diagram of the block, the incline. Normal force points here, and gravitational force points here. If we set our axes like so, oh, by the way, there's friction pointing backwards. That's important. We find out that the x component of gravitational is mg cos theta. And since it moves along the incline, these forces end up summing to 0, which means our normal force just ends up being mg cos theta. By the way, we can find out that because the block is moving this way and frictional force is pointing the opposite way, this angle ends up being 180 degrees, which means that this just ends up being -1. Now back to friction. We know that the force of friction is calculated by the coefficient of kinetic friction times normal force, and we already found out what normal force is. So really, this entire equation ends up being 1/2 kx squared plus 2x mg sine theta minus mu k mg cos of theta times 2x, because it travels that distance, equals 0. We can plug in x for here and get that km squared g squared sine squared of theta over 2kx squared plus 2m squared g squared sine theta over k is equal to 2m squared g squared sine theta cos theta over k. We can combine both these fractions, and I need to erase some stuff, then more room. We can combine these fractions, and we end up getting that 5 m squared g squared sine squared theta over 2k is equal to 2m squared g squared sine theta cos theta over k. And now we can evaluate for uk, which has been throughout the entire problem and I forgot to mention. Now, m squared cancels out, g squared cancels out, sine cancels out only by 1, and we end up getting a cos in the denominator, and that just evaluates the tan theta. The k's cancel out, the 2 multiplies the denominator by 2, so we end up getting 5/4 tan theta is equal to mu k, and that is our final answer.